Hi, I'm Jeff Groh, and this is Partial Differential Equations. To this point in the lecture series, we have solved some pretty interesting problems using Fourier analysis. However, we've deferred some of the technical details of mathematical analysis that we'll try to remedy here. We'll begin with a definition. Let us have a collection of functions. These functions map some domain in Rn into R. We say that the sequence Fn converges pointwise to a function f, which has a similar domain and codomain, if for each point within the domain this, as a sequence of real numbers, converges to this. Fn of x converges to f of x for each fixed x. This means then that for each fixed x, you'll have maybe some given epsilon, but the delta that you obtain will depend not only on the epsilon, but also on the x. So you'll get a different delta at different values of x, even if you have the same epsilon. So it may converge faster in some parts of the domain than others. I should also emphasize that for this to be pointwise convergent, it has to converge at each x within the given domain. If there's an x where it doesn't converge, even if it converges at all other values of x, including neighboring values of x, it still does not converge pointwise. Example. Remember the function f of x equals 1 between 0 and 1/2 and 0 on the domain, the interval from 0 to 1. We had the Fourier series 1/2 plus the sum, as n goes from 1 to infinity, 1 over n pi, 1 minus -1 to the n, sine of 2 pi n x. Now consider the sequence Gn of x, where we take this partial sum How do we get convergence? Does Gn converge to f, pointwise anyway? As we saw, this function here looks like this, whereas this function, these converge to this function, which looks a little different. It has the value of 1/2 at 1/2. And so this sequence of functions does not converge pointwise to this function on the entire interval from 0 to 1. However, if we consider the domain D to be 0 to 1/2 union 1/2 to 1, then it does converge pointwise on this domain. We get convergence on the domain 0 and 1 except the point at 1/2 despite the Gibbs phenomenon. If the original function is like this, well, if the function that we can actually converge to pointwise is this, we'll have these Gibbs phenomena where we overshoot, pass through the midpoint, and overshoot on the other side as well. But the region where we overshoot gets narrower and narrower as n increases, and so these additional points will be picked up converging pointwise when big N gets large enough. Some Fourier series converge better than others. Consider f, which maps -1 to 1 into R, defined by f of x is the absolute value of x. And the graph is obviously this. I guess we should add in these endpoints here. We'll consider as our Fourier basis 1 over the square root of 2 cosine n pi x sine n pi x, n going from 1 to infinity. Now, a naught is the inner product of f with 1 over the square root of 2. We'll integrate from -1 to 1 the 1 over root 2 times the absolute value of x. Well, the integral from -1 to 1 of the absolute value of x is 1. So we'll end up with a value of 1 over the square root of 2. To calculate the ANs, we'll take the inner product of f with the cosine of n pi x. We'll have the absolute value of x times this cosine. And because of the even nature of both of these factors, the integrand will be even, so we may as well just double the integral from 0 to 1, x times the cosine of n pi x. If we integrate this by parts, u is going to be x, 1, and 0. We'll have cosine n pi x. We integrate down this side. So when we integrate cosine, we'll get sine, but we'll have a 1 over n pi. Integrate again, we'll get -1 over n pi quantity squared. We'll get twice. We'll have x over n pi sine n pi x plus on this one, minus on this one. Minus a negative is plus 1 over n pi quantity squared cosine n pi x, evaluated, of course, from 0 to 1. If we evaluate at 1 on this first term, we'll have a factor of 1, but that's not the really important part. The important part is we'll have sine of n pi, which is 0. Similarly, when we plug in 0, we'll get 0. So this term cancels off. We'll have, when we plug in 1, we'll have cosine of n pi, which is -1 to the power of n, and we'll be subtracting cosine of 0, which is 1. So I'm going to write this as -2 over n pi quantity squared, and then 1 minus. I'll reverse the order of the subtraction, and that's why we get the negative out front here. So these are the ANs. For the BNs, we take the inner product of f with the sine of n pi x, and again that's the integral from -1 to 1 of the absolute value of x, which is an even function, times the sine of n pi x, which is an odd function. If you multiply an even function with an odd function, you get an odd function, and so we get 0 for all of those. We didn't normalize the basis in this case. So let's take the inner product of 1 over root 2 and 1 over root 2. Well, I guess that is normalized. How about our cosine n pi x and cosine n pi x? We can double the integral from 0 to 1, but we still need to use the half-angle identity, which has a factor of 1/2. We'll be integrating across an entire period for the cosine, which gives us nothing. And so, again, we get 1. To see how this works, I've plotted here with n equals 1, which is not very many terms in this Fourier series. And you can see we get, well, what doesn't look to be a very good approximation to the absolute value function. But at n equals 3, we get a slightly better approximation. It gets really bad right here towards the origin, but it's pretty close to a straight line when we get farther and farther away. Come back up here and change this to n equals 5. It's even better. It looks like it's rather uniformly close, except here at the origin where we have this sharp turn, but everywhere else, it doesn't stray very far from the straight line. And as we get bigger and bigger values of n, it gets tighter and tighter about those straight lines. At 20, you can see that it's getting closer, but there's kind of an absolute upper bound on the error that you can see for each of these n's. For n equals 3, the biggest the error is going to get, looks like here at 0, maybe at 1 and -1 as well, but in between, it's going to be some small deviation across the entire line. There's no Gibbs phenomenon here because the function is continuous. N equals 5, again, kind of a uniform bound on the error for all the way across the entire interval. Of course, if n gets really big, it looks pretty tight, pretty close to the absolute value function at n equals 100. So as you can see, the approximate solutions do something like this, where we stay within these nice bounds all the way across. We could almost say that there's a uniform gap that the solutions stay in. And for the larger values of n, that becomes even closer, even a smaller gap that they stay within. You can see that for different values of x, given an epsilon, you can choose the same value of n, so that if n is bigger than n, we'll stay within that epsilon bound. This is a kind of uniform convergence. For pointwise convergence, we say that given x in the domain and epsilon greater than 0, there exists some n in the set of natural numbers such that if n is bigger than n, then the distance between fn of x and f of x is less than the given epsilon. So that defines pointwise convergence from before, but there's another convergence form that we can talk about, and that's uniform convergence. Uniform convergence should be independent of the x. Given your epsilon, you should be able to find the n independent of the x. So you'll have this nice uniform distance being close for each of those x's. So our definition may be something like this. We say that the sequence Fn converges uniformly to some function and write Fn converges to F uniformly if given epsilon greater than 0, there exists n within the set of natural numbers such that if little n is bigger than big N, then the distance between Fn of x and f of x is smaller than epsilon, and that is for all x within the given domain. We should say that it converges uniformly on this domain if this set of conditions holds. The problem with our function f of x equals 1 and between 1/2 and 1 we have a value of 0 is that our Fourier series gave us something that converged to this. And we had this Gibbs phenomenon where we had this big jump, and that jump stays big no matter what you do. To try to mollify this, you're going to have this Gibbs overshoot on both sides. The way to get a kind of uniform convergence in this case is to back off from the discontinuity at 1/2, and then you can get uniform convergence on these intervals. So we'll go from 0 to B1, where B1 is less than 1/2, and from B2 to 1, where B2 is greater than 1/2. You can see that if you back off from discontinuities, you can still get uniform convergence. What we're really dealing with is a series of functions and we want to know, does the series converge uniformly? i.e., for each x, the series will converge. If for any fixed x, it'll converge if it converges as a sequence of numbers. But to converge uniformly, we need to get convergence with the same, given an epsilon, with the same n for all of the x within the domain. Now, in other words, we want to know, does this converge uniformly to some function? And it turns out there's a simple test. It's called the Virustras test, after the famous mathematician Carl Virustras. And it's pretty easy to check. It goes like this. The series sum as n goes from 1 to infinity, Fn of x converges uniformly on some domain D to F if, first of all, the functions themselves must be bounded by some constant. Different functions may be bounded by different constants. But to get that uniform convergence, we need the sum of these bounding constants to add up to some finite number. So this series has to converge. Another way to say this is the terms in the series as functions must be bounded, and the bounds must be summable. For a proof, consider that conditions 1 and this is for all x within the domain, and 2 so these adds up to some finite number, imply that for each fixed x, the series is absolutely convergent. Which implies that it converges. Therefore, we define f of x to be the value of that sum for each fixed x. The only question that remains is, does this converge uniformly to this function f? So we consider the difference between f and the partial sums and see if we can get this to be small independently of x. But this is the sum, since this is the limiting value of these, this will be the sum of the tail, which, using the triangle inequality, is less or equal to the sum as n goes from n plus 1 to infinity, the absolute value of fn of x, which is bounded by the sum as n goes from n plus 1 to infinity of the mn's. Now, since the sum of all of the mn's converges, and these are positive terms, the tail end of the sum has to get small, as small as you wish, so that given any epsilon greater than 0, there exists some n hat in the set of natural numbers. The sum, as n goes from n hat to infinity of the m sub n's, will be smaller than epsilon. So you can get as tiny as you want in the tail. Also note that this n hat is independent of x. And therefore, we get uniform convergence. The sequence of functions, the series of these functions, fn of x equals e to the minus nx sine of nx, will converge uniformly, and we can show this pretty easily. The sum of these will converge uniformly because fn of x's are all bounded by, sine is bounded by between negative 1 and 1, so an absolute value gets no bigger than 1. The exponential function e to the negative nx on the interval from 1 to infinity has its biggest value at e to the negative n. So these are our mn's. Do these constants sum? Do you get a finite value for this series? The answer is yes. It might be easier to see if I rewrite it in this way, because now you can see that this is geometric with a common ratio of 1 over e. And since the common ratio has a magnitude less than 1, this will surely converge. Therefore, this series in X converges uniformly on the interval 1 to infinity. However, let me say, but not on 0 to infinity. So why does this series converge uniformly on the interval 1 to infinity, but not on the interval 0 to infinity? And the answer is pretty clear. If you plug in 0 for x, e to the 0 is 1. So all of these constants will end up being 1, and that's not summable. Uniform convergence is special because of the following theorem. If let's suppose the sequence of functions, these are continuous on some domain D, and 2, Fn converges uniformly on that domain D to some function f. The conclusion is f is continuous on that domain. You can see now why our step function couldn't get uniform convergence on the entire interval. It had to converge to something that's not continuous. So yeah, you might be able to get some convergence on uniform convergence on intervals where you back away from the discontinuity, but otherwise you can't get uniform convergence on the entire thing. For proof, we'll let epsilon greater than 0 be given. Now, since these functions uniformly converge to f on D, there exists some natural number n such that if n is bigger than or equal to n, then the distance between fn of x minus f of x is less than epsilon for all x in D. Now, we're going to fix some point x naught in the domain, and note that since each of these fn's is continuous, there exists some delta greater than 0 such that if x is to within delta units of x naught, then the distance between fn of x naught and fn of x will be smaller than epsilon. Now, to show the continuity of f, note that the distance between f of x naught and f of x is less than or equal to the distance between f of x naught and fn of x naught plus fn of x naught and fn of x plus fn of x and f of x. Now we know we can get close in each and every single one of these. We had an epsilon divided by 3 here. we said epsilon for these, but we can use epsilon divided by 3 just as well. And so this will be less than epsilon over 3 plus epsilon over 3 plus epsilon over 3 equals epsilon, and therefore it is continuous. We deduce that Fourier series that converge uniformly converge to a continuous function. Also, if f is not continuous, its Fourier series does not converge uniformly. We have the Gibbs phenomenon in this case. Let's suppose that Fn converges to F uniformly, and also these are continuous. Then the integral converges, as a sequence of numbers, converges to the integral of the limit. That is, if you take the limit of these integrals, n goes to infinity, you get the same thing as if you put the limit on the inside. We call this convergence in the mean. The integral is an averaging process. You'll recall that the average on AB of some function is, by definition, 1 over b minus a, the integral from a to b of f of x dx. And that's by definition. So to find the integral is very much akin, off by a simple constant, the length of the interval, to the average. So in other words, uniform convergence of continuous functions gives you convergence in the mean. As a proof, let's set Mn to be the max for x values between a and b of the difference Fn of x minus f of x. Now, note that because these functions are uniformly convergent, if we were to take the limit of these mn's, they would have to go to 0, because the functions uniformly, the fn's uniformly approach the function fx on the interval. So now let's look at the difference of the integrals. Which you can, of course, write as a single integral Now the absolute value of the integral is less than or equal to the integral of the absolute value. These are less than or equal to mn, and that's equal to mn times b minus a. The mn's go to 0, you'll recall, which means the difference between the two integrals must go to 0 as n goes to infinity. And that's the end of the proof. So if the functions converge uniformly, then the integrals will converge as a sequence of numbers. Now the same cannot be said for derivatives. Let me give you fn of x equals, say, sine of nx divided by n. This will converge uniformly to the function that is identically 0. However, let's look at f prime n of x. If we take the derivative, we'll get n times the cosine of nx all over n, which is cosine of nx, and these functions don't converge at all. You have points in the domain where you just keep oscillating back and forth and don't settle on anything. So the sequence of derivatives will not converge to anything at many points in the domain, whereas the derivatives of the zero function are 0, which that has no problem with definition at all. So derivatives don't necessarily give you convergence, even if the original convergence was uniform. Integrals do. So what is it going to take to get those derivatives to converge on the given interval? Suppose that we have functions fn. Let's suppose that these functions are C1. Remember that functions are C1 if they are continuously differentiable. They're differentiable on the given interval. Let's suppose our interval is AB, and the derivative exists, but the derivative is also continuous on that interval. Let's suppose that these converge uniformly to some function f on AB, and let's suppose that these functions have derivatives that converge uniformly on AB. Then the function f that these things converge to is differentiable, and what is more, the derivatives will converge uniformly to f prime on AB. So what went wrong with the last example? You had uniform convergence, the functions were C1, but you didn't have uniform convergence of the derivatives. Those things didn't converge at all at many points. And so you couldn't claim that the thing it converged to, in that case the zero function, was differentiable even though it was, but you couldn't claim that that convergence was uniform because it didn't converge at all to that function at many points in the domain. So how are we going to prove this? We'll not assume that fn primes converge to f prime. We're going to let fn primes converge to some function g pointwise. We'll consider that convergence pointwise to begin with. We know it will converge pointwise in this case. We'll take a look at the limit on n as n goes to infinity as the integral from a to x of fn prime of t dt. Well, by the fundamental theorem of calculus, this will be the limit on n of fn of x minus fn of a. These fn functions converge uniformly to f, so we'll have f of x minus f of a. On the other hand, because of the hypotheses of this theorem, we remove the limit inside, but that gives us the integral of g of t dt. Now remember, g is continuous by a previous theorem. And that implies that the integral from a to x, g of t dt, is differentiable. But remember, this function this differentiable function, is equal to the difference between these two. This is constant. So this function, f of x, must be differentiable. Now, by the fundamental theorem of calculus, this equals this. We'll just take the derivative of both sides. On the right-hand side, the derivative of the second term is 0 because it's constant, and so you get f prime of x. So g of x is, in fact, f prime of x, and that is the thing that the n primes will converge to then. And that's the end of the theorem. As another example, let's suppose fn of x is the sine of nx divided by n squared. Then these things are bounded by 1 over n squared, and this is summable. So by the Virustras M test, the series converges, and it converges uniformly. So note that these derivatives are going to be the cosine of nx over n, and these converge uniformly to the function that is identically 0. We deduce then that the derivative of the series is equal to the sum of the derivatives. Remember that a series is really the limit of the sequence of partial sums. And so we're thinking of this as the limit of the sequence of partial sums of the terms involving cosine of nx over n. We have a number of theorems to finish up this section on analysis. First, I'd like to recall the Bolzano-Virustras theorem, which says that a bounded sequence of real numbers has a convergent subsequence. And the picture is fairly simple. Suppose we have something where we have an upper bound m and a lower bound little m, and we have a sequence of numbers sequence of real numbers. These numbers are bounded. They lie within some range of values on the y-axis here. And the idea being that if we have a sequence of real numbers that is bounded, lies within the bound, like this, we can construct a subsequence of those that get, say, bigger and bigger, monotone increasing. We can have a monotone increasing and bounded sequence, and that subsequence then would have to converge. I'd also like to define what I mean by a sequence being Koshi. If given epsilon greater than 0, there exists some natural number n such that if both m and n are bigger than n, then the difference between an and am will be smaller than epsilon. So a sequence is called Koshi if you choose any level of closeness that you want, any epsilon greater than 0. Eventually, adjacent terms or nearby terms in the tail can be no more than epsilon apart. However, there's a famous theorem a sequence converges if and only if it is Koshi, which may be surprising to you, but this is a classic characterization. And the proof is pretty easy. First, we'll assume that the sequence converges and then prove that it is Koshi, and then we'll do the alternative. So we're going to suppose that the sequence an converges to some number a. Well, we can use the triangle inequality to trap both of these smaller than epsilon over 2. Eventually, both n and m, bigger than some n, big N, we'll have to trap these less than epsilon over 2, and hence it is Koshi. We have only to prove the other direction. To prove the other direction, we'll need the following lemma. A Koshi sequence is bounded. And to prove this, we'll start off by saying, suppose epsilon is 1. The sequence is Koshi, so we can talk about the difference between, say, an and an. Now this will be smaller than epsilon, which is 1, but you can also see that this will be bigger than or equal to the difference in absolute values, and that's greater than or equal to the difference without the absolute values. We'll push this term over, and we'll have the absolute value of an plus 1. And so you can see that values in the tail of the sequence will be at least bounded by this value. All we have to do is set m to be the maximum, and we'll take a list of all of those from before. including this last value. Then each of these will be bounded by this m. So back to our theorem, we'll suppose our sequence is Koshi. Our goal is to prove that the sequence converges. But by the lemma, this is bounded. So by the Bolzano-Virustras theorem, this must in fact have a convergent subsequence. So we'll suppose that we have A and K, and this sequence will converge to, say, a bar. So given any epsilon greater than 0, you can find an n such that if A and K is greater than n, then the difference between the A and K's and a bar will be smaller than epsilon. We'll let m be also greater than this n. We get less than or equal to am minus a and k minus a bar. Now, we can bound each of these by epsilon over 2. This one because we're a Koshi sequence, and this one because we get convergence of the subsequence. And we get convergence. We have one more lemma to prove before our main theorem. We'll call this Aubel's lemma. And it goes like this. Sn is going to be a sequence of partial sums for some sequence bk. We'll assume that the 0th partial sum is 0. M is greater than n is greater than or equal to 0. Then we'll look at the sum as k goes from n plus 1 to m of terms of the form a sub k, b sub k. And it turns out this will be a sub m s sub m minus a sub n plus 1 s sub n plus the sum as k goes from n plus 1 to m minus 1, a sub k minus a sub k plus 1 s sub k. We begin our proof by noting b sub k is the kth partial sums minus the k minus first partial sums. That will just add on that kth term. So we'll begin with the left-hand side, and making this substitution we can re-index this last sum so that they'll both have terms s sub k. But to do that, we have to replace k minus 1 with k. We'll have a new index. K will be the old k minus 1. So you can see then that when we plug n plus 1 in, here we would have n plus 1. We'll have the following. We have these two sums now. They both begin and end at different places. So we'll peel off the last term here and the first term here. And we'll be left with the sum left with this. And that's the end of the proof. We now present the theorem that we have been working towards Dirichlet's test for uniform convergence. We'll suppose that sequence AN has positive terms. The terms are monotone decreasing, and they go to 0. There exists some positive real number m so that the sum is bounded, and this is going to be true for all x and for all of these n's. These are the hypotheses of the theorem. Now for the conclusion. Then the series converges uniformly on the interval AB. What's important, and perhaps a little stunning, is that the above does not assume that these functions are continuous. Suppose that we had this thing as monotone decreasing, so this difference must be greater than 0. And of course, the nth partial sum will be the sum of the first n terms of this series. We'll now look at the sum from n plus 1 to m and at this point we apply Aubel's lemma. We now assume the fact that, first of all, these are non-negative, and these are bounded. When we bring the absolute value into this sum, we'll get a bound here. And now this last sum is telescoping. So when you plug in, you get a lot of terms that will be canceling out. You don't get this term here canceled out. And that simplifies in this way. Now, since the terms involving an go to 0, that implies then that the original series converges. And so the sequence of partial sums is Koshi and hence converges. So that we can set g of x to be the limit of this partial sum. We have then and we've already shown that on the right-hand side that's bounded by since the ANs go to 0, we may be bound by some epsilon greater than 0 here, which then is independent of x. And that implies uniform convergence. We're now done with the heavy analysis of this section, but we do have a few little theorems to throw out there. If x is not 2k pi, then the sum of all of these signs of k times x, what does that add up to? It adds up to the cosine of x over 2 minus the cosine of n plus a half times x all over twice the sine of x over 2. The left-hand side is sometimes referred to as the conjugate Dirichlet kernel. Note that if x is an even multiple of pi on the left-hand side, you just get 0. There is a part 2 to this. Where we start off with a 1/2 term and then the sum of the cosines of k times x. In this case, you get the sine of n plus 1/2 x over twice the sine of x over 2. Note that if k is an even multiple of pi in this second case, these add up to n, because you get positive 1 on each of those, so you get n plus a half on the left-hand side. The left-hand side here is called the Dirichlet kernel. We'll multiply by twice sine of x over 2 on the left-hand side of the first formula. We're going to use the fact that twice sine A sine B is the cosine of A minus B minus the cosine of A plus B. So using this identity, the first term gives us the cosine, the difference, x over 2. On the next one, you add them. For the next term, you subtract and then add. All the way down to the end, where we'll have the cosine of the difference cosine of the sum. And you can see we're going to get a telescoping sum and all you have to do now is divide both sides by twice the sine of x over 2, and that completes the proof. The second identity is proved in a similar fashion. Now if we look at the sum, as k goes from 1 to n, by our identity, we had the cosine of x over 2 minus the cosine of n plus 1/2, all times x, all over twice the sine of x over 2. The two terms in the numerator are both bounded by 1. We'll consider this x value to be between 0 and 2 pi. So we can see that these partial sums will be bounded provided that x stays away from certain places, which makes the denominator equal to 0. In other words, we have to be apart from the endpoints of this interval, away from 0 and 2 pi. I should probably turn this around so that b is bigger than a. We can apply all of this theory to a series of this form, and we can get uniform convergence provided that these decrease monotonically to 0. So for example, we can look at all of these series and deduce that these all converge uniformly as long as we're on the interval AB which is a proper subset of the interval from 0 to 2 pi. We're going to have to stay away from the endpoints, in other words. And note also that at least on the endpoints on this last series, we get divergence, in fact. If you plug in 0, that series diverges. Same thing when you plug in 2 pi, cosine of an even multiple of pi is going to be 1 as well. So you end up with the same series, you get divergence at the endpoints.